Hi, welcome back. For this video, we are going to continue on with related rates, and we're going to take a look at some more real-world applications. In this example, we have Bilbo. He is tired of carrying a ring, and he throws it into a nearby lake, causing ripples in the form of concentric circles. So they're giving me a shape right here, circles. They tell us that the radius of the outer ripple is increasing at a rate of 2 feet per second. When the radius is 4 feet, we want to know at what rate is the area changing. This is a perfect example of a related rate. So the first thing we're going to do is list out the givens. So what do they tell me? That the radius is changing at a rate. Anytime we see a rate, that's a rate of change for us. That for us means a derivative. So they're telling me about the change in radius. D stands for change in radius with respect to time, because they tell me 2 feet per second. 2 feet per second. When the radius is 4 feet, they're asking us at what rate is the area of the water changing. So now they're telling us what to find. The change in area of the water. So there's a lot of information there that they gave us. Now once I list out everything I'm given, now I'm going to come up with a geometry formula that has area, radius, and circles. And of course you're thinking area of a circle. You are correct. Area is pi r squared. Now once we have this part, now we're ready to do the calculus. Now remember, the area formula for us, this is kind of like our position function in calculus, in physics. But what we want to find is the change in area, which is the velocity function, kind of like. So we talked that we've done this earlier. If you take the derivative of position, you get velocity. But remember, we're going to take the derivative with respect to time. Or in this case, t. So when I take the derivative of area, that's going to give me dA dt. If I took the derivative with respect to w, it would be dA dw. Likewise, over here, we take the derivative. Be careful, pi is just a constant. I'm just going to drop that 2 in front, and I'm going to get this 2 pi r, but now I got a chain rule with the derivative of r, dr dt. No one would be like dr, but you know, but we're taking the derivative with respect to t this time, so we get dr dt. And this is my velocity equation. Now, all we have to do is to solve for dA dt is plug everything in. So I can now say dA dt is 2 pi. My radius, which they tell me is 4, dr dt, which we know is 2, and I can just kind of type all this in. 8 times 2 is 16, so we get 16 pi. But let's now talk units. One thing I love about Leibniz's notation is how it works so well with units. For example, A for area. Well, what are we measuring area in? Well, it's going to be feet, but area always has a feet squared unit. T is my time. Well, what are we measuring time in? That's per second. So we should get 16 pi feet squared per second. And there's our answer. So what this is saying is as water is increased, so as we drop water in here, water is now increasing at a rate of, the area is increasing at a rate of 16 pi feet squared per second. So we're going to write this as a sentence. The area of the circle, the area is, it's positive, so it is increasing at a rate of 16 pi feet squared per second. And that's going to be our answer. Now, increasing because our rate of change is positive. So let's do a rule here. If the rate of change is positive, we are increasing. But greater than 0, we are increasing. If the rate of change is less than 0, we are decreasing because we're getting smaller. Now, also, are we moving towards something or away from something, which we'll talk about later on. So let's talk about Luke. While enlarging a square photo for his Snapchat app, Luke went a little overboard. He determined that the area of the picture was increasing at a rate of 4 inches squared per second. Oh, that the area of the picture was increasing at a rate of 4 inches squared per second. So again, a related rate. At what rate were the sides increasing when the sides were at 3 inches? So I'm going to list out my given. So in this case, he's telling me the change in area. Now, it doesn't specifically say the change, but they do mention the word rate. And for rate, remember, this is a rate of change. So they're telling me the change in area of the picture, dA dt, is 4 inches squared per second. Next, at what rate are the sides increasing? Well, what do we call the sides of a square? I don't know, I'll call it L. Are 3. So at what rate are the sides? So when the sides are at 3 inches, so the sides are at 3 inches. And we're asked to find the rate at which those sides are increasing, or what we want to call dL dt. It's the change in the side length with respect to time. Remember, we're talking about a square here. L, 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 L. So what's happening is this picture is blowing up here. And at a certain given time, the area is increasing by 4 inches squared per second. We want to find out what are these sides increasing by at that exact moment. So we have to come up with an equation that has area, sides, and the square. Of course, that's area of a square. Area is length squared. So this is like my position. To get the velocity, or to get dL dt, we're going to need the derivative here. We need the derivative. With respect to t, we get dA dt, and that's going to equal 2L dL dt. And from here I can just plug everything in. dA dt, 2L, they're telling me is 3, and dL dt is 4. And I can just write this all out. This becomes 6 times 4, which is 24. I messed that up, didn't I? Whoops, so sorry. Sorry. I messed that up big time, so look at this. I just deleted it all. So be careful. They're telling me dA dt is 4, 2L, and I'm looking to find dL dt. L, they're telling me is 3 still, so I can write this as 2 times 3. dL dt, and then I can divide. dL dt, this becomes 4 over 6. Well, what are we measuring L in? L is going to be in inches. Time here is measured in seconds. So we can say that the length of the sides, that these sides are increasing, spell it out, at a rate of 4 over 6 inches per second. And there's your answer. Very easy to do. Sorry about messing that one up so badly, but we went back and fixed it. Notice I made a mistake. Mistakes are going to happen. I knew I made a mistake when I had A, and I'm like thinking inches squared, but I want L, which I knew my units should be in inches. So I knew I made a mistake right there, and I went back and I fixed it. So it's okay to make mistakes. You're going to make mistakes on these. Don't panic about them. Just fix them. All right. So next example. Mr. Warnow is full of hot air. He decides to blow air into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius. So look what we're trying to find here, dr dt, when the radius is 2 feet. So I'm going to list out my givens. The first thing is I'm blowing air at a rate of 4.5 cubic feet per minute. Wow, that's just my change in volume right there. That's dV dt, because it's cubic feet per minute. So they're telling me dV dt is 4.5 cubic feet per minute. They also tell me that the radius here is 2 feet. What we're asked to find is the rate of change of the radius. So they're asked to find dr dt. Dirt it. So I need the volume of a sphere. So I'm going to go and give that to you. 4/3 pi r cubed. There's the volume of a sphere. Notice we only have one variable here. That's an r. So when I take the derivative, it's a related rate. I'm looking for dr dt. Drop the power of 3. That becomes 12/3, or just 4 pi r squared. Chain rule, dirt it, dr dt. I just plug everything in. 4.5 equals 4 pi. The radius is 2, which just becomes 4 when I square it. dr dt. Don't simplify, just leave it alone. We're going to get dr dt equals 4.5 over 16 pi. Well, what do we measure radius in? That's why I love this thing. What do we measure radius in? Well, in this case, it's just going to be in feet. It's a single unit. Time is, in this case, minutes, so feet per minute. So we would say that the radius at this point is increasing, spell it out, at a rate of, and you can write this out, 4.5 over 16 pi feet per minute. And there's your answer. Easy peasy. All right, last one here. All right, this one's not on your homework tonight, but I want us to start seeing it. From a distance of 4 miles away, Ray watched as her parents abandoned her. Their spaceship was traveling vertically at a speed of 2 miles per minute. When the ship reached an altitude of 3 miles, how fast was the angle between the ground and the ship changing? So let's see here. You always want to draw a picture if you can. Here's Ray. Her parents abandoned her. She is 4 miles away from where a rocket ship is taking off vertically, like so. There's our rocket ship. When the rocket ship reaches an altitude of 3 miles, we want to find out how fast is the angle between the ground and the rocket ship. So this angle right here, we want to find how fast this angle is changing. So this one's going to blow our minds here. Ready? So the first thing we're going to do is I'm going to list out all the givens. 1, they tell me how fast the rocket is traveling vertically at 2 miles per minute. Well, that's not really helping. Well, that's just telling me that this side right here is changing at 2 miles per minute. So I'm going to have to give everything here a letter. I'm going to call this, let's call this one A. This is B. And I'll call this C. Now, I know from experience that C is just going to be 5 miles. That's a 3, 4, 5 right triangle. So they're telling me how fast the rocket is traveling vertically. Well, that's my change in B. dB dt is 2 miles per minute. And what they're asking me to find is this d theta dt right there. That's what we're being asked to find, d theta dt. So how do we get d theta dt? Well, we got to think trigs. Unfortunately, anytime we have this, you got to think trigs. So here's what I'm looking for. I am going to use the following two. I am going to use tangent. And the reason I'm going to do that, I'll talk about this in a minute. But see this right here? Her distance isn't changing. It's a constant. Not a constant. It's a constant. Therefore, I know the rate of change in A has to be 0. And that's going to help me. So when I write out the tangent of theta is going to be b over a. Note, I'm going to give everything a variable. Even though there are numbers to it, I don't care about the numbers. I just want the variables for now. This is my position. But now I got to take the derivative. The derivative of tangent is secant squared theta d theta dt. And this is where our constant will be really helpful for us. Because a is a constant, I can write this as b over 4, or just 1/4 times b. And that's going to make our derivative easy. See, this right here, quotient rule. This right here, power rule. Much easier to do. So when I take my derivative, I'm going to keep the 1/4, but this becomes db dt. I took the derivative of b, I get db dt right there. Now I just got to plug everything in. And it's going to look nasty. I mean, I do have to know what secant squared is, so I need the secant of theta. Well, the secant of theta is just the hypotenuse over the adjacent. The hypotenuse we said is 5, the adjacent is 4. So this is 5 over 4 squared d theta dt, 1/4. Well, what's db dt? Ah, that was that 2 that they told us earlier. And I can solve this. D theta dt, this becomes just 1/2 times. This is 25 over 16, but I got to flip it, and I get 16 over 25. Convince yourself that is correct. And if you reduce it, you get 8 over 25, but let's talk units. Theta is always in radians. Time in this case, minutes. So we can say that the angle is positive, is increasing at a rate of 8 over 25 radians per minute. And there's our answer. So when we're doing a related rate, 1, draw a picture. Label that the parts that move with a variable. Like notice here I put a variable on the b here. If the part does not move, you can replace that with a constant. And that's what we did with the distance right here. That 4 was a constant. I was able to just replace my constant with a 4. I can just replace it. Write the equation that relates. So in this case, we use tangent. Take the derivative with respect to t, which we did, and then solve for what we wanted, d theta dt. All right, hope you guys enjoyed the video. I'll see you soon. Bye-bye.